All right, so we'll get started here. I think it would be good for me to do another example, kind of continuing what we did last time. We were a little bit hurried at the end, and I want to explain to you what's going on there. So I want to talk about roots of unity again. So the roots of unity, well, here's the notation. So like last time I introduced this notation, like 1 over n. And what that is in the complex setting is actually a set of values. So this one, it actually is the following. It is e to the 2 pi I over n, such that, oh, my bad, I'm missing a k here, raised to the k power, okay? Such that k equals to, let's say, 0, 1, 2, all the way out to n minus 1. So what that looks more explicitly like is this, 1, and then, because 0 gives you e to the 0, which is 1. And then you have e to the 2 pi I. Well, let me write it this way. Then you have zeta n, and then you have zeta n squared, all the way out to zeta n to the n minus 1. All right? Where zeta n is e to the 2 pi I over n. This is the so-called principal nth root of unity. And if you want it in terms of like real things, it's cosine of 2 pi over n plus I times the sine of 2 pi over n. So these are the n complex numbers that all of them, if you raise to the nth power, you get back the number 1. So let me just show you how this works. Let's just work our way from n equals 2 and on up. N equals 2, zeta 2 would be e to the 2 pi I over 2, right? That's e to the pi I. What is that? Well, that's cosine pi plus I sine pi. But what is that? Well, sine of pi is 0. Cosine of pi is minus 1. So the principal second root of unity is just minus 1. All right, so what this means is that 1 to the 1/2 power is two things. It's got 1 in it, and it's got minus 1 in it. Those are the two complex numbers which square to give you 1. All right? That's the k equals 0 case. It is definitely, I think you'll agree that 1 squared equals to 1, right? And minus 1 squared equals to 1, right? So n equals 3, what's this look like? Well, then zeta 3 is, e to the 2 pi I over 3, which is cosine 2 pi over 3 plus I, the sine of 2 pi over 3, right? So that's 120 degrees around the unit circle. And so what that gives you, I draw a picture of it. It's like here-ish. So I believe that's minus 1/2 plus I square root of 3 over 2 when you look at the values of that. All right? Well, that's the principal third root of unity. What is the answer here? I'm having a discussion. So I don't know. There's really not an answer here. I'm trying to relay information, So, but I know we get so locked into this problem solution mentality, right? But you got to understand sometimes in like higher math courses, we have discussion, discovery, right? So there's not a problem I'm solving. I'm sharing information, There's lots of different problems we could look at. But anyway, so this is one principal third root unity. Also this thing. And what's the other one? Where's where's zeta 3 squared go? Remember we learned last time that if you multiply zeta 3 by zeta 3, it rotates it by the standard angle, right? So that means that zeta 3 squared is going to be another 2 pi over 3 around, right? So that's like down here. Zeta 3 squared is down there. So the other one is minus 1/2 minus I squared of 3 over 2. So these are the three complex numbers whose cube is 1. And I, of course, could also draw the other one 1 here. Here's 1.
So this is just the principle. So you're using the top, which was for everything else.
Yeah, the e to the 2 pi I over n generates the rest of them by taking powers. The picture for n equals 2 is more boring. It's just there's 1 here, and there's minus 1 here, right? But you should start to notice that they're like symmetrically arranged around the origin. If we get n equals 4, we have zeta 4 e to the 2 pi I over 4, which is e to the pi I over 2, which remember is cosine pi over 2 plus I sine pi over 2. So zeta 4 is I. K is just running from 0 to n minus 1. So it's just keeping track of the fact that there's more than one of them. So in this one, here, the fourth roots of unity, you got 1, you've got I squared, and you've got I cubed. Of course, you can simplify that, 1, I, minus 1, minus I. And if you draw the picture here, it's very satisfying. 1, I, minus 1, minus I. These are the fourth roots of unity. Fifth roots of unity. I won't try to give you the Cartesian components of them. I'll just kind of give you a picture because we can graph it, right? E to the 2 pi I over 5, that's the principal fifth root of unity. If I draw a picture of it, you've got 1 here, right? And then what is 2 pi? It's like 360 over 5, which is what? 360 over 5 is 72. So you got to rotate about like 72. 72 times 2, 144. So that's like over here-ish, right? Again, plus another 72. I don't know, it's down here somewhere. Something like this. They should be symmetrically arranged. And by the way, all the roots of unity have length 1. I can prove that, by the way. So these, this is zeta 5 squared, zeta 5 cubed, zeta 5 to the 4th. Each time you go another 72 degrees around the unit circle.
What happens when you get, will it ever repeat itself?
Yeah, once you get to, yeah, this is, zeta 5 to the 5th is equal to 1 again.
And then when you go zeta 5 to the 6th, it's going to be the...
Right. Yeah, there's always, it keeps, I mean, you could put k as an integer here, and you'd get the same set of values. They just loop back on each other. So I list k going from 0 to n minus 1 just to give a distinct list. Anyway, these are the principal roots of unity. And so this is very weird, right? Relative to your experience with real variables, right? Because you've been taught before what is 9 to the 1/2 power. Is 3, right? So before, 9 to the 1/2 power is equal to the square root of 3 is square root of 3, listen to me, square root of 9, which was 3, right? But in this new story I'm telling, I'm hijacking the notation, the 1/2 power, and giving it a different meaning than the square root. And this is common in complex variables. In here, now, in the complex setting, the square root of 9, well, that's still equal to 3, actually. But 9 to the 1/2 is the square root of 9 times, square root of 9 and minus the square root of 9. So, like, more generally, the nth root of z is the principal nth root of z, and then, like, zeta n times the principal nth root of z, and then zeta n squared times the nth root of z, zeta n to the n minus 1, the nth root of z. And here, the principal nth root of z is defined to be the real nth root of the length of z, and then e to the 2 pi I theta over n, where theta is the the angle of z. All right. So I wrote this in a previous lecture. I'm just bringing it out again. But what I'm trying to tell you is something weird going on here, in the sense that I'm making a distinction between these notations, right? And now the half power includes all possible solutions, all possible complex numbers that square to give you 9. Wait a minute, yeah, square to give you 9. So 3 and minus 3. Now, all right, so I said this has something to do with factoring, right? Do you guys remember the factor theorem? What's the factor theorem say? What did the factor theorem say? The factor theorem said that if it said the polynomial, right, f of x has factor x minus c, right, if and only if what? F of c is 0. So every 0 gives you a factor, and vice versa. So consider, if we look at f of x, say equal to x to the third minus 1. Right? What's it mean for that to have a 0? So like f of c equals to 0 is the same as c cubed minus 1 equal to 0, right? Which is the same as what? C cubed equals to 1, which I believe, if we allow c to be complex, means that c is an element of the third roots of unity. So that means that these guys I wrote down here are zeros of this polynomial, which means I can factor f of x like this: x minus 1, x minus 1/2 plus I root 3 over 2, x minus minus 1/2 minus I root 3 over 2. Now, you might not recognize that right offhand, but let me just show you how you would have found that in pre-calculus algebra. F of x equals x cubed minus 1. So that's a special form trinomial. We do x minus 1 and x squared plus x plus 1, right? But then we complete the square on this guy, x plus 1/2 squared, and then we have to subtract a fourth. 1 minus a fourth is minus 3/4. Which then we have the difference of squares. If we look at this as, instead of looking at minus 3/4, we say minus 3/4, well, that's actually I root 3 over 2 squared, right? There's, that's a plus. Sorry about that. So we'll put a minus on that side. And then the point is, that factors into x minus 1, x plus 1/2, plus root 3 over 2, x plus 1/2, minus root 3 over 2. I lost my eye. I can't see. Let's see here. Sorry, that's horrible. I. So that is how we would have discovered the complex factoring in pre-calculus algebra way, right? Complete the square, yeah, special form trinomial. But if I asked you to do this for like the x to the 5th minus 1, that would have been a very nasty question to ask in pre-calculus algebra. But now it's a piece of cake. If I ask you to factor, I mean, with this newfound toy I'm sharing with you, if I asked you to factor, you know, f of x equals x to the 5th minus 1, well, you'd be like, well, I can use the 5th roots of unity because those are all zeros for this. So it's like x minus 1, x minus the 5th root of unity, x minus the 5th root of unity squared, x minus the 5th root of unity cubed, x minus the 5th root of unity to the 4th power, and we're done. That's a factor. That is a factory. And it's no accident, right, that the roots of unity have to come in conjugate pairs because they provide factorizations of like a real polynomial. Remember, real polynomials have zeros which come in complex conjugate pairs. There's always this balancing, right? For every, like the conjugate of zeta 5 squared is zeta 5 cubed. The complex conjugate of zeta 5 is zeta 5 to the 4th. They always come in conjugate pairs unless they're real. So there's a lot of really neat patterns to see here is all I'm trying to tell you. So now that I'm done with my show and tell, let's actually calculate the principal nth root of unity for like a specific complex number, which is a little bit ugly. Any questions?
My only question would be like actually putting a number in for z. So if you had
yeah, we can do that. Sorry if do you guys, am I get a race? Okay, so your textbook actually does have this stuff in it, but I think I'm probably talking about it in a slightly more sophisticated way than the textbook, but whatever. So let's, an example. Let's see here. How about z equals to 3 minus, I don't know, 3i. Let's calculate the nth root of this, all right? So the modulus of z, the length of it, is the square root of, what, 9 plus 9? That's the square root of 18. I'll just leave it like that. What's the angle of z? standard angle, what is that? Let's draw a picture. What are we looking at here? We're 3 over, and we're 3 down, aren't we? So what's the standard angle here? You could go all the way around like this, right? Whee! And say it's 315 degrees, I guess. Right? 270 plus 45. Or, yeah, because it's on the equal x and y means it's 45 degrees. Or you could just go clockwise, 45, right? So I think the good choice here to make is minus pi over 4. All right? We work in radians, all right? So the first order of business, really, when you're calculating the principal, like nth root of something, is to find the polar form of the complex number. That's what I'm doing at the moment. So the polar form of this complex number, right, is just z is equal to the square root of 18 times e to the minus I pi over 4. See right there? This is the polar form of 3 minus 3i. And we can do all kinds of neat stuff with that, right? For example, z squared is 18 e to the I pi over 4 squared, right? Which is 18 e to the minus I pi over 2, which, by the way, is minus 18i. Because e to the I pi over 2 is I, and e to the minus I pi over 2 is minus I. I'm doing this, e to the I pi minus I pi over 2. But something I didn't show you guys yet, another thing you can do with a complex number is it makes it really easy to calculate reciprocal. Remember, to calculate the reciprocal in the Cartesian notation, we had to do the multiply by the conjugate over the conjugate thing to figure it out. It's much easier if you know the polar form. See, because 1 over z is what? 1 over the square root of 18 e to the minus I pi over 4, right? How do you put this in polar form? How do you put that in polar form? Well, you guys know how to move exponentials from denominators to numerators, right? What do? You flip the sign of the argument, right? Like 1 over e to the 2x is like e to the minus 2x, right? So same pattern here, 1 over square root of 18 e to the I pi over 4. So I cannot sing the praises of how the polar form of a complex number allows you to calculate all kinds of arithmetic things for it pretty easily, And you can always go back to the Cartesian form once you're done with the calculation too, right? Like, what's the Cartesian form of 1 over z? To find the Cartesian form, we just go, okay, that's 1 over the square root of 18. This is cosine pi over 4 plus I sine pi over 4. And of course, you know what those are, right? 1 over root 2, 1 over root 2. So explicitly then, this is, 1 over the square root of, what's 2 times 18? 36 plus I, 1 over the, hey, that's kind of cool. Look at that. So apparently 1/6 plus I over 6 is the Cartesian form of this. Okay, so I did say I was going to find the principal nth root, right? So let's do that. I haven't done that yet, have I? How do we do it? Oh, thanks. Where did I put my chalk? Oh, yes. So let's see here. The principal nth root of z, I'm still working with the same example, right? So we do square root of 18, the nth power of that, all right, nth root of that rather, and then e to the what? What was my angle? Minus I pi over 4. I mean, this is my theta. I can't write up here. So pi over 4 is the theta, yeah? And then I divide by n. No, the nth root, which I've sadly deleted now, erased. Modulus is so the length, the nth root of the length of z times e to the there's no 2 there. It's just I theta over n, where z is length of z e to the I theta. All right. If I put a 2 pi in the previous formula, that's bogus. That shouldn't have been there. We'll never know until I watch the video later. But at that point, it'll be too late, won't it? So this is what? This is the square root. Let's see. What is that? I think that's the 2nth root of 18. Right? If n was 3, you'd have a cube root of a square root. That'd be a 6th root, for example. That's just a real number, whatever it is. And then over here, e to the, minus I pi over 4n. Now, let me be specific here for a second. Let's look at the 4th roots. I like 4 because the 4th roots of unity are really easy to write out, So, all right, so the 4th root of z would be the 8th root of 18, whatever that is. I mean, you can calculate that in your calculator, easy. And then e to the what? E to the minus I pi over 4 times 4, 16. Okay, and then in contrast, the 4th roots of z, it's a set of 4 things. It's this thing, it's the 4th root of z, which I've written right above. And then it's I times that. And then it's minus I squared times that, which is minus it. And then minus I times the 4th root of z. So, this is multiplication by 1, multiplication by I, multiplication by I squared, multiplication by I cubed, respectively, of the principal 4th root. And there's a pattern here in terms of like the graph, very similar to what we already did. First of all, the 4th root, it's at minus pi over 16, so that's like, I don't know, in here somewhere, right? Where's the next one? It's at I times that, which is a counterclockwise rotation of 90 degrees. So it's like here. And then minus it is over here. And then another 90 degrees down here for this one. So what we're looking at, this would be like the principal 4th root of z, and then, the same distance. What is the distance to these points? It's what? All of these points are distance, the 8th root of 18 from the origin. Something I have yet to emphasize, but I should have, is like if you have the polar form of a complex number, what's its length? So if W is the length of W, this is stupid, let me not say it that way. Let me say it's R e to the I beta, right? And you calculate the length of that. What's the length of W? R is a real number here. The length of W, right? It's the square root of W bar. That was the formula, right? What's that look like? Well, that's the square root of R e to the I beta, right? R e to the minus I beta. I'm assuming R is real. What happens to the I beta and the e to the minus I beta? They cancel, right? They give you e to the 0 because I beta minus I beta is 0. Those are reciprocal. And you're just left with the square root of R squared, which I guess would be the absolute value of R. But for the sake of, we should assume at the outset that R is greater than 0, right? And if we do that, then this is just equal to R. So my point to you is if we have something as a number times an imaginary exponential, the length of that complex number does not involve the imaginary exponential. The imaginary exponential just points that complex number in a particular direction, just gives you the direction of the complex number. This is how this works. But you see how this shifts, right? Like before we had nth roots of unity, so they're always starting at the x-axis and rotating around. But that same separation between answers happens in general. When you're looking at like the nth roots of a complex number, you find the principal one, and then you rotate by 2 pi over n to find the next one, and the next one, and the next one. Just that. So obviously, like you see why we don't do this in earlier courses, right? In fact, you're going to forget about this once you're past this course. We don't do this in calculus. All right? Like no one does this in calculus. This exists in this particular section in the trigonometry book, and it's typically forgotten after that. Why? Because we don't respect Gauss, who said we should be doing this as like our default 200 years ago. I don't know. Why don't we have nice things? This is a question we can ask. But it is more complicated, right? It is more sophisticated. But the neat thing is, incidentally, it is a very fortunate coincidence that the quadratic formula works out as it does. It does that because the principal second roots of unity are 1 and minus 1, which makes that whole plus minus square root thing actually adhere to this like deeper discussion of nth roots. So that's something you can. That's a homework problem in like the complex variables course if you want to take it. But anyway. All right, so I think I've said my piece about complex variables in here as far as I can think of. I'll read the section in your book again, see if there's something I missed. But I think what I've told you should be enough for you to do the homework problems I'm going to give you, which then will be the basis for quiz problems. Okay? So with that, let us return to graphing with polar coordinates, yeah? There's actually, so I was looking, something I left out, my bad. And I don't know, it just kind of slipped through the cracks, and I don't know where to put it. I mean, I should tell you about it, but this is kind of an odd topic for us here at the moment, but here it is. So something I missed. I missed Heron's formula. Heron's formula for oblique, for area of oblique triangle. What's an oblique triangle? What's that? It's a triangle where at least one of the angles What is it? What'd I do?
No, I'm not, that's something else, I'm sorry.
Oh, you're fine. I found the most amazing set of politically incorrect videos. I'll tell you after I stop taping. It is the most politically incorrect thing I've seen on YouTube in some time. And there are many of them. I have been partaking in them. Anyway, okay, so if this has side length A, B, so oblique means one of the angles has to be larger than 90 degrees. Yeah. So, like this angle here makes it oblique, right? And the perimeter is A plus B plus C, right? So there's something called the semi-perimeter, which they use S for, and that's the perimeter divided by 2. And here's the weird thing. And I actually don't know a derivation of this right off. I mean, I think I might be able to derive it with like calculus 2, but that's definitely not what I should be doing in here. So, and your book doesn't seem to have a proof of it, and I have not searched the internet to see how this is proved. I don't remember seeing its proof anywhere, as far as I can decipher. But this is the formula for the area of such a triangle. It's dimensionally consistent because you've got the product of length times length times length times length. That's length to the 4th power. You take the square root, that gives you a square length squared. Hey, that's area. So it's at least dimensionally consistent. That does not prove why this formula should be. Another nice feature of this, it's symmetric in the role of the signs. The sides, like A and B and C, play the same role. That makes sense. If you think about this kind of triangle, or triangle, so that kind of symmetry makes sense. Again, that's not a proof. So here's how to put it in practice. An example. Woohoo! Suppose we have length 7, 10, and 15. Right? So the semi-perimeter then would be what? 7 plus 10 plus 15, that's 22, that's 32. 32 over 2, which is 16. So then if we believe Heron's formula, the area here is the square root of 16 times 16 minus 15 times 16 minus 10. It doesn't really matter what order you put them in. Just make sure you don't use the same one twice. 16 minus 7, right? Which is the square root of 16 times 6 times 9, which is 12 root 6. Because square root of 16 is 4 and square root of 9 is 3, so 4 times 3 is 12, and root 6. And then that is approximately 29.4. So I will say, in terms of formulas to quickly find the area of a triangle, it's pretty nice, right? What's the other competitor for finding the area of a triangle? What if we know an angle? What did we learn before? If this is A and this is B and this is theta, what was the angle? What was the area of this triangle?
Wasn't it A times B cosine theta?
So this right here would be B sine theta, right? This guy. And so A is the base. This is the height, so 1/2 base times height, right? But the height is B sine theta. So you're in the ballpark. It's sine, not cosine. So 1/2 AB sine theta. I'm awful tempted to try to prove this formula using like law of sines, because law of sines relates like side lengths to angles. And I better not. No good can come of me trying to prove this on the fly, right? All right. So the polar graphing. See, I can't start polar graphing here. We've got 8 minutes left. There is no way I can do justice to it. So if you don't mind, I'm going to show you something that's really off the rails, all right? So let me tell you a little bit about my research that I've been doing with students. Since about like 2012 or so. And so one of the principal examples that we've looked at in there, was it over here before? Did you move it?
I think I did move it back.
So we already got Heron's formula?
No.
Oh, well, let me do that. Let it sit here for a second. All right, it should be relatively easy to find. So I've been studying how you do calculus over algebras. All right, so and I typically use the letter A for that, all right? So for example, if you take A equals to the complex number system, the calculus that results, we have a course for that called complex variables. Most universities do. I'm teaching it next semester. So this is a standard material. And when you look at calculus over complex numbers versus calculus over real numbers, the theory of calculus over complex numbers has many features that the real number calculus doesn't have. All kinds of magical things happen. There are calculations which are possible in the complex numbers calculus which are just not possible in the real numbers. It's very special. There's a lot of structure there. But one of the number systems I've been looking at over the years of my students is what I call H. This is, and I call it the hyperbolic numbers. Hyperbolic numbers. And so just to give you a quick tour here, it has things of the form A plus B J, such that A and B are real numbers, and J squared is 1. So we've been looking at complex numbers where we adjoin I, where I squared is minus 1, right? And so this leads to some very weird things. For example, here's one of the weirdness. How about this? If you do 1 plus j times 1 minus j, what do you get? So the usual laws, it's just like complex numbers. You just multiply like usual. This gives us 1 plus j minus j squared. So the j and the minus j cancel. What's j squared equal to? 1. 1 minus 1? 0. This is 0. So what we're looking at here is the product of two non-zero things equals 0. Does that ever happen with real or complex numbers? No, never, right? There's no such thing as what's called a zero divisor, right? This does not happen. And this makes proofs of calculus in the hyperbolic numbers way, way more complicated. Also, when you study the, well, anyway, we don't have too much time, but one of the things we noticed that's really neat is if you look at e to the j theta, that has a meaning in this hyperbolic number system. And e to the j theta, turns out, is cosh theta plus j sinh theta. But in contrast to the complex number system, you can write anything in the form of a polar, the polar representation. We're good anywhere, right? Even the origin, if you're willing to give up on the uniqueness of the angle, you can just say, well, that's where the length of z is 0, right? That's the origin. Everything else, right? In this, if you look at the hyperbolic plane, it's really weird. You've got these, so this is like multiples of 1 plus j, multiples of 1 minus j, along the lines y equals plus or minus x. And so if you just have something of the form, say, number, let's call it rho, e to the j theta, it only will cover things in there. So like the natural attempt at like sort of a polar coordinate system for the hyperbolic numbers, it only gets you just that sector. So like one of the things I've been working with my student Heron is trying to, that's funny, is trying to sort of extend this idea to the other 4 sectors. And we kind of have a sort of an ad hoc way of coming up with polar coordinates, quote unquote, over the whole hyperbolic plane. But it involves, you have to think about the 4 different sectors and like study how they move from one to the other. It's really a pain. You say, you might wonder, like, okay, so like why, who cares? Well, for me, I'm just very interested in understanding how calculus works in the most abstract way, in this sense that I can. So like complex numbers have been very successful. If you go on in engineering, you can use complex numbers to do something called conformal mapping. You can solve what's called Laplace's equation. So in electrical engineering, if you want to fit, have voltage, have a plate with fixed voltages around the boundary, if there's no charge in the middle, this gives you Laplace's equations with a boundary value. And you can use conformal mapping to solve that problem. So complex analysis naturally solves problems with Laplace's equation. Hyperbolic calculus naturally solves problems with the wave equation. That's what I would argue. So like the Laplace equation for hyperbolic numbers is the wave equation. And I don't think it's widely known or understood how you would do the analog of conformal mapping for hyperbolic numbers. And you could think about that idea for other number systems as well. So these, another interpretation, you see these, I don't know if have you guys ever seen special relativity? Thought about relativity at all? In relativity, you talk about the light cone. So there may be a way to, in fact, there are papers written about this, identifying these zero divisors as being like the future and past light cones. So, but anyway, if you haven't ever talked about relativity in any of your other courses, never mind. But anyway, thank you for bearing with me. That's just a sense of where I'm currently working with a student. But in the past, I've had students basically go through like Calculus 1, Calculus 2, differential equations, and trade real numbers for an algebra and like see what they could do. So anyway, thanks guys.